Prioritizing the general anatomy of muscle, the structure of muscle, and that's really going to help us understand the contractile machinery within the muscle that really allows muscle movement. Okay, it's a very unique apparatus on the microscopic level of muscle that brings about shortening of the entire muscle body, and that's what we're going to look at, starting with the structure. So we spoke about the neuromuscular junction when we look at the somatic nervous system, and that was the division of the nervous system that innervated skeletal muscle. Right? So there's three types of muscle: there's skeletal, there's cardiac, there's smooth. Now, cardiac and smooth were innervated by the autonomic nervous system, whereas skeletal is the only division that is voluntarily controlled. So that was innervated by your somatic nervous system. Now, when you look at the neuromuscular junction, we saw that a motor neuron innervated muscle at the motor end. So what happens after that innervation? So we saw the activities at the neuromuscular junction, and we're going to pick up from here and look at what happens after that end potential. Right, so first we'll start by talking about the structure of muscle. Muscle is usually attached to two bones. Two bones, for example, the biceps brachii that you saw in your anatomy lab is passively attached to your scapula proximally and your radius distally. There are some exceptions where muscles only attach to the skin, such as the muscle of the face, or cartilage, such as the muscle of the larynx. Now, there's a connective tissue sheath that's wrapping around the entire muscle, including the tendon, and that's called the epimysium. Epimysium. And if we strip that away and look inside the muscle body, we saw many bundles of muscle fibers that form a muscle fascicle, and that fascicle is covered by the perimysium, right? Another connective tissue sheath there. Now, if we took a fascicle, right, and we stripped away that perimysium and we looked inside, we will see several muscle fibers. And a muscle fiber is synonymous to the muscle cell. And when we use those terms, it's changing. When I say muscle fiber, it means muscle cell. It's the same thing. It's the structure or functional unit of the muscle body. And the muscle fiber is again wrapped in a connective tissue sheath called the endomysium. So let's recap that. We have a single muscle fiber, this is synonymous to the structural unit of the muscle, the muscle cell. It's covered by the endomysium. Several muscle cells group together to form a muscle fascicle, about 100 to 1,000, and that is covered by the perimysium. And then muscle fascicles come together to form the muscle belly or the muscle body, and they are wrapped, including the tendon, by the epimysium. Now, when we look at the structure of a single muscle cell or a single muscle fiber, it is multi-nucleated. And that means it has more than one nucleus. And in that way, it differs from your traditional cell. The reason it's multi-nucleated is because during the embryological period, several muscle cells fuse together. Now, also different with the muscle cell is that the nucleus is peripherally in the cell. So the nucleus is closer to the outer surface of that fiber or that cell. Now, two structures we already saw already, which is the plasma membrane. In muscle, it's called a sarcolemma. Okay, so when I say sarcolemma, that is synonymous with the plasma membrane. And then there's the cytoplasm of a muscle cell, and that is called the sarcoplasm. Okay, so these terms are synonymous with those of a traditional cell. They're just different in muscle. The sarcolemma is the plasma membrane of muscle cell or muscle fiber, and the sarcoplasm is the cytoplasm. All right, let's go even deeper. Let's look at the structure of a muscle cell here. Now, muscle cell contains myofibrils, and myofibrils are really the important part of the muscle fiber. This contains the contractile mechanism, or contractile that allows this muscle to shorten. We can look at that in much more detail. It also contains the sarcoplasmic reticulum. The sarcoplasmic reticulum is synonymous with the endoplasmic reticulum of a traditional cell. That's where calcium is being stored. The only differences here are that it's going to wrap around these myofibrils. So this was the myofibril, like this structure, and the sarcoplasmic reticulum wraps around that. There's also lots of mitochondria. So there's an abundance of mitochondria. You see them interspersed between these fibrils, and mitochondria is going to be essential to muscle tissue. It's going to be producing the ATP that's required for muscle to contract. Now, throughout the muscle, right, on the periphery, there's a structure called a T-tubule, right, this green structure. And it's some channels, essentially. And they're gonna deeply invaginate, so you can see them one here, the structure of the muscle fiber. So a T-tubule is a channel that runs through the depth of the muscle fiber. It's gonna go all the way through the depth of that muscle fiber. And its job is going to be to transmit the signals, maybe calcium, that is important for muscle contraction. Now, as a result, on either side of a T-tubule, there are two structures called lateral sacs. And these are basically modifications of that sarcoplasmic reticulum. Okay, two structures called lateral sacs. Now together, a T-tubule and the two lateral sacs on either side forms a triad. I'll say that again. So we have a T-tubule that's running through the depth of the muscle fiber. Right? That is going to transmit the calcium, but where's it going to get the calcium from? On either side of a T-tubule is associated with a modification of the sarcoplasmic reticulum called lateral sacs or terminal cisternates. Those two terms are interchangeable, and these are going to form a triad. And again, this is how calcium is going to be released from the sarcoplasmic reticulum and move throughout the muscle, and that's going to be essential for muscle contraction. Now, if we look at the structure of a myofibril, so we said that a myofibril, so again, just to recap here, this is a single muscle fiber, this entire structure. It's synonymous to the muscle cell. If we look inside the cell, there are several structures, right, that are called myofibrils, and these are subcellular structures. And they are made of repeating protein units. Okay, these filaments are made of repeating protein units. And together, those units form a sarcomere. We'll see what that looks like in a minute. But essentially, a sarcomere is the arrangement, the neat, orderly arrangement of two protein filaments, actin and myosin. So actin and myosin are going to alternate each other, right, and form a sarcomere. And this is what is going to give muscle a striated appearance. So skeletal muscle has that striated appearance because of the sarcomere, which is formed by actin and myosin. Any questions so far? Okay. So we're going to draw out a single sarcomere. And I want you to bear in mind that a sarcomere is just one part of that continuous myofibril. So many sarcomeres are running along the length of a myofibril. Okay, so. So a myofibril equals many sarcomeres. So we're going to draw one sarcomere here. Okay, we're going to draw it as a cut surface or cross section. And if we took a cross section here, we could see two alternating proteinous filaments. Right? One was thick and one is thin. One is called the thick filament and one is called the thin filament. All right. Okay. Now, when the first histologists that studied muscle looked at muscle, they described muscle based upon different staining patterns, okay? And they named various zones based upon the presence or absence of that actin or myosin, right? So along the center, we have our myosin. Okay, this is myosin. And this is forming the thick filament. I'll label these out in a minute. All right, so this is your thick filament along the center of the sarcomere. Now on either edge, so on the periphery of the sarcomere, we have the thin filament here. Okay. So I'll just label this here. This is your thin filament. And this thin filament is made of actin. Okay. Your thick filament is made of myosin. All right. Now, there's an area along the periphery of the sarcomere, and that's where all the actin filaments are conjoined together. And that forms the Z line. The Z line. And again, this is based on the histological reference of looking at muscle under the microscope. So the Z line is that area where all the actin filaments are joined together. And you can see they form a Z-like configuration. And on the other side is also a Z line. Now, Z line to Z line is a sarcomere. A sarcomere is from one Z line to the other Z line. Along the center, right, where myosin is connected, that is called the M line. That is called the M line. And this is going to be the center of the sarcomere. Now, along the outer edges or the outer limits, and I'll sort of border this here, we can only see actin here, okay? And so histologically, this region stains much lighter, much paler. And we call this region the I band. Right, the I band. And this is the area where we have only actin filaments, no overlap with the myosin filaments, okay? So that is your I band. Similarly, along the center here, I'll sort of border this out, where we only have thick filaments, there's no overlap with our thick filaments, that is called the H zone, right? The H zone. Okay. So the I band is the outer periphery of the sarcomere, and that's only actin filaments. The H zone is the center of the sarcomere, right around the M line, and that is only myosin filaments. Now there's one more area that we're gonna label, and that is where actin and myosin actually do overlap, right? So actin and myosin do overlap across the I band. I'm sorry, the A band. Let me draw this just above here. And that is the A band. Okay. Now, if we look at the head or the myosin filaments, okay, and I'm going to use myosin filaments interchangeably with thick filaments. Okay, they're the same thing. The thick filament is formed by myosin. Similarly, the thin filament is interchangeable with actin. The thin filament is formed by actin. Okay, so this is your thin filament. And this is your thick filament. Now, if you look at the head of the thick filament, there are some out progressions or out projections. And this is the outward sticking head of the myosin filament. And I'm going to call that the cross bridge. And we're going to see how this cross bridge, right, this head that's sticking out from myosin, is going to reach down and interact with this actin filament. And that's essentially the apparatus that drives muscle contraction. So I want you to bear these structures in mind. We have the thick filament formed by myosin, the cross bridges, which are the heads of those thick filaments. We have the thin filament formed by actin, okay? We have the Z-line, the connections of those thick filaments along the periphery of the sarcomere. We have the M-line, the connection of the thick filaments along the center of the sarcomere, all right? And we have the I-band, which is the staining pattern of just actin, right, just actin. The H-zone, which is the staining pattern of just myosin. And then the A-band is where actin and myosin overlap. Okay. Any questions? Okay, that'll probably make a little bit more sense as we continue on here. Okay, so let's just recap those structures that we talked about. So this is the histological staining pattern of muscle. So you took a piece of muscle, and put it under a microscope, okay, and you zone in on one sarcomere, and from D-line to D-line of a single sarcomere. You see these different staining patterns. Along the center is the M-line. This is where the myosin filament or the thick filaments were connected. Along the Z-line is the outer periphery of the sarcomere. This is where your thin filament, so your actin, is connected. Okay. Now this region here is a little bit deeper staining because there's overlap. This is your A-band. This is where the thin and thick filaments overlap. Whereas if you took this area, just myosin here, it's a little bit paler staining, and that's your H